All right, guys, let's see how this goes. We're going to deal with some linear and quadratic functions. So first thing we're going to do is just identify those functions based on what we're given here. So which of the following are polynomial functions? Those are not polynomial functions. State the degree, leading coefficient. For those that are not, explain why not. Okay, so here's what we got. So polynomial function means that we can identify exactly what degree we're talking about and everything else. So I'm looking for the degree of 3, 1, and 0. So the degree of the polynomial is going to be 3 because that's the greatest of them. So this one does happen to be a polynomial. The lead coefficient is positive 4. Okay, so that means this is a positive odd. Remember, all your odds, if we have to talk about end behavior, that seems to work like a line. So we could talk about the end behavior as well, since we have that happening. In part B, so this thing right here, so this actually means 6 over x to the 4th plus 7. And since we have our variable in the denominator, this is not a polynomial. Okay, so this is no good. As we look at our next one here, we're dealing with the square root over top of all this stuff. So I get 9x to the 4th plus 16x to the 2nd. Okay, and it would all be to the 1/2 power. So we're no good here. Remember this, since we're adding in here, I can't simply distribute this. So I'm not even going to draw an arrow because that's not okay. We'd have to work completely differently around this one. So this is not going to be a polynomial. D definitely is, right? Because we're kind of running out of options here. Again, this is a degree of 1, degree of 4. So if I look at the degree, it is 4. That's the greatest of the two. And if I look at my lead coefficient, so 4, remember this is even. So that means the polynomial itself is going to have end behavior like a negative parabola. So it's going to be down, down as we try and tie all of these ideas together through the course of the year. All right, so some vocabulary that we have 0 function, right? That means that we're going to end up with a degree of 0. And we had, what would that be? That would be y equals 3, right? So we end up with nothing. There's nothing we can do with it. We can say y equals 0. So deal with it either way. As soon as we put a x to the 1st power, so y equals 2x, right? So that's now constant. Oh, wait, got ahead of myself. That's going to be linear. Let me undo that. Okay, so constant means I get just plain old 2. We get that number. Okay, so the 0 function had to be a 0. Linear function, y equals 2x. And now the pen's acting funny. There we go. Quadratic function, that means we want to add in a squared, so 2x squared. All right, sorry about that. That pen thing was bothering me. All right, so we have quadratic. Now, keep in mind, I also threw this in here because if it's quadratic, that doesn't mean that it doesn't have a linear term or it doesn't have a constant function on top of it. But what happens is we're going to name it or label it based on the highest degree. So we have undefined, we have 0, 1, 2, and obviously we could work through the 3rd power being cubic. We've been through a lot of those things. All right, so linear functions and their graphs. So we have y equals mx plus b. We have point slope form as well, one of my personal favorites. And of course we have standard. And we know how to graph from all of those things. So the only difference now is we can have some ordered pairs written in really weird ways. Okay, so we know what's in place, and here, right, that means whatever the function is, if I put in -1, I get 2. So I might just steal those and pull them out here and say 3, -2. Now I'm told that this is a linear function, so we want to write the equation. So the first thing we're going to have to do is find the slope. So I'm going to start with -2 minus 2. If I start with -2, I have to start with 3 plus 1. So I get -4 over 4, or just -1 for the slope. And if it says to write the equation, I'm going to choose the easiest one, which is point slope form. So let me just tell you which one I'm going to use here. So I'll highlight those. So I have y minus the y value. So I'm going to go with plus 2, -1 times x minus the x value. So that would work. If I need to translate it into any other form, we can distribute and take care of those items as needed. Okay. So the big thing here was Notice this is going to be your ordered pairs. So we're going to change how we show you the information. You're okay with that. All right. So the Camelot Apartments bought a $50,000 building. And for tax purposes, they are depreciating it $2,000 per year over a 25-year period using a straight line depreciated. Okay, so they're telling you this is to be linear. What's the rate of change? So here's the thing that's going on is we want to find out a couple different numbers. So at year 0, it was $50,000. Okay, and they're using a slope depreciating $2,000. And for linear, that means the slope is negative 2,000 to that value. And that's for the first 25 years. Okay, what's the rate of change for the building? Well, we just found out that that's the slope. Write an equation so we can find it quickly. Okay, so y equals negative 2,000 and the number of years. So we'll use x plus 50,000. Okay, got an equation. We found out the slope, evaluated 0. Okay, so at 0, we know it's going to be 50,000. And then at 16, so we're going to plug 16 in here and then take that away. So we're at what, negative 32,000. So we should be at 18,000. Okay. And then the last thing we're going to do is we're going to do this and solve in reverse. So take my equation right here, my linear equation. I'm going to find out when it's going to be 39,000 equals negative 2,000x plus 50,000. Okay, so we'll subtract the 50,000 and divide it by negative 2. Okay, so subtract, we're at negative 11,000. Negative 2,000x divided by negative 2,000. Okay, so these numbers seem a little bit intimidating, okay, only because they're all in thousands, but we don't really need to use any of it because we're going to reduce all the zeros out. So that means 5.5. So it'd be 5.5 years until the building is worth $39,000. All right, so again, a lot of the things that you've already used and just trying to present it in different ways. So we just have to make sense of all those things. So X being years and Y being the price. And it's all based on the value that it was bought at for the whole thing. Okay. Tax purposes. For tax purposes, you want your building to be worth less. All right, so slope M, rise over run. Remember, rise, the y-axis does the rising, so that's the easy way to remember those. And of course, we did have y equals mx plus b. All right, so we can use those. Not everything is going to be super straight line stuff, so that's why we have some scatter plots. So quick, I just dropped these in here. So scatter plots, that means we're dealing with x, y, right? So a set of ordered pairs, and then we're just trying to get these things to find out if they have a correlation. Okay, as we added in Algebra 2, and I'll highlight these, we can not only call it a positive correlation, but we can call it strong versus weak. Okay, and we could say that there is no linear correlation. That's when we have a whole mess. And again, even for negatives, we can say it's strong versus weak because we do see an upward trend versus a downward trend. And it's all based on how closely all those points are related. If everything seems like an outlier, that's where you get that no correlation. All right, without having to look at it, one thing that we talk about in some Algebra 2 classes, based on everything going on, I don't know if we got to all of them, the correlation coefficient, so R. So this is one thing you can get right off your calculator as long as it's in the diagnostics on. So that's one thing we'll talk about in class if you don't have it yet. R is always between 1 and -1. It can be inclusive, so it could actually be on 1, and it could be on -1. And here's what happens. If R is positive, okay, if R is positive, that means you should have some type of positive linear correlation. If it's negative, it should be negative. All right, and what it means now. So now we dropped it to absolute value. So the closer I get to 1 or -1, that means I end up with a strong correlation. So something like 0.98, that would be a strong positive correlation. Negative 0.972 is still pretty strong. Okay? The closer I get to 0, think of 0.221. Okay, this is getting to a weak correlation. So if I have this number, I don't really need to look at the graph to be able to say, oh, that's strong or weak. what I would be able to do is determine based on the numbers. So if I had negative 0.015, I would know without looking at the graph that this is weak, and it's so weak I would probably call it a no correlation because it's almost zero. Almost zero. All right. So I know we've done a lot through Algebra 1 and Algebra 2 to deal with scatter plots. So we're going to give you this problem here. I do have a review video off to the side if you need it on how to put those things on. And it does also put in here that if you don't have your diagnostics on, if you follow the steps here in the yellow highlighter, we can do that. So you want to pause now, go through the X's and the Y's, and we're trying to figure out what's going on, predict weekly sales if the price dropped. Did you pause yet? Okay, so use your resources. We want to get through those. That should be a review. All right, welcome back. The next thing we're going to do is deal with transforming square root function or the square function, quadratic functions. And this one should go relatively simple based on what we've just talked about. So we know this is up 3. We know it's upside down. And if I multiply it by 1/2, it's in parentheses because that's the way it was in the textbook. But it's really just 1/2. So that means it's going to be vertically compressed. Okay, so that means I'm going to go up 3. That's the only translation we have other than being upside down, and these two go together. So I'm going to down 1 and over 2, down 1 over 2 for its reflection. So we're going to show this parabola has been vertically compressed. All right, in part B, we have down 1, we have left 2, and we have a vertical stretch, but it is positive. So let's go left 2. So left 2, down 1. Gets us our first point, vertically stretched by 3, 1, 2, 3, and its reflection. So we get all this information to get a pretty little graph. Okay, remember we have all these other things going on. We have the axis of symmetry that runs right down through there. That's an x equals, and it's going to be x equals -2 because that's what it goes through. So we can get a lot more information, and that's what we're going to delve into today. All right, so if you want to check, so if you weren't watching the video and you want to double check, there they are on the right. All right, so we've dealt with standard form. Normally we're factoring to get things out of here, but the things that are important, things that we already know, the A value is still going to tell you vertical stretch, vertical compression. It's going to tell you positive or negative. It's going to tell you whether it opens up or down. And the other thing we get from the C value is we're going to get the y-intercept, right? If we make x 0, we'll get that y-intercept right away. But what I can't get from standard form is the vertex very easily. That's why we have such a thing called the vertex form. Now the vertex form, we're going to get the vertex is HK. That's why we always use the opposite of the inside. We'll get the A value. Again, that's going to tell you vertical stretch, vertical compression, up or down. It's going to tell you all those things. But what I won't get really easily from it is being able to factor it or do anything else for x-intercepts. And I also won't get a y-intercept very easily unless I plug some zeros in and do some work because I have squares and all sorts of stuff. But that's that basic given information. Okay. So how can I get from one to the other? Well, if I take negative b over 2a, that's going to give me h. And if I plug that in, I can get k. Right, so that's going to be kind of that crossing over of how we can get that information. If I want to get from vertex form into standard form, I'm going to follow the order of operations, which means I need to square this, which means we're going to FOIL it. Then we're going to distribute A, and then finally add K to that result. So I think that's what we're up to now as we review some of those ideas. So vertex HK, x-intercepts. So here we have the quadratic formula. We could definitely use that. And here's what we're saying. That C value at a standard form is pretty important to us. All right, so let's do this. Let's go with FOIL, distribute, and collect. So that means I want to FOIL this. I'm going to use -2, x plus 3 times x plus 3 plus 4. I do want to do this first. I could multiply the -2 in, but I want to do that in the end just because it makes this part of it a little bit easier. So I get x squared plus 3x plus 3x plus 9, right? Because you have first, outside, inside, and last. So I get x squared plus 6x plus 9. We're going to multiply it by -2. I am not forgetting about my plus 4. It looks like I easily could. And I've seen it happen. All right, -2x squared minus 12x minus 18 plus 4, -2x squared minus 12x minus 14. Okay, that was quick. Because I assume that we're doing pretty good with foiling, and that shouldn't be a big deal. All right, so that's how we get that thing changed out. So that one's order of operations, not a huge big deal. Okay. Most of the time that you spent, you were dealing with -b over 2a to find this information. So if 6 is b, I'm going to use -6 and 2 times -3. Okay, so I get -6 over -6. So the b value, the x value vertex, so h equals 1. So far for the vertex, I have 1, and I'm trying to find out that other part of the information. So that means I'm going to plug 1 in here. So 1 squared is 1. 1 times -3 plus 6 minus 5. All right, these will always be half of each other. So I get, not 6, I get 3. So I get -2, so the vertex is -2. So can I write it in vertex form now that I know the vertex? Sure can. Y equals, or f of x. The a value is -3, doesn't change. X minus 1 squared minus 2. Right, and if I FOIL this, multiply by a -3 and subtract 2, I can easily check it to check these back and forth. Okay, now it also says I can do this by complete the square. We'll deal with that in class. Not everybody likes complete the square. So I'm going to give you one solid method, and then we'll add that in our pair deck. All right, what else can we do with it? So, excuse me, just like we had linear regression above, we can use a quadratic regression. Okay? And we have Galilei and Newton. They had some awesome stuff. They talked about vertical velocity. So that means even though we have something that is free falling, okay, so let's say this acorn dropped from the sky. Right? If we just look at the straight vertical velocity is what their height position of free falling is what these two gentlemen were talking about a long, long time ago. As you can see, I was born just after that, so I didn't get a chance to meet them. But in this table, again, we're going to go back to the calculator, and instead of picking a linear regression, you're going to pick a quadratic regression in the next to last step. So if we plug this in for x and for y, we'll pull this data. We'll believe this data was done by somebody that was doing an experiment, and it should give us our first equation. And then what happened is we check that r squared value. It is an excellent fit. And then here's the only new thing that we want to take a look at. Okay, so free fall theory says that if you take the opposite of g, which is that a value, right, and then we divide it by 2, then we're going to get closer and closer to that 9.8 meters per second squared. Okay, I think our science department may have something in feet as well. I think it's somewhere near 16 feet, just because we work here in feet. Okay, so again, just another chance to talk about free falling objects and how we can find out how close we can get, because we're talking about a linear. So notice we're down to t to the first power as we make this transition. So we've reduced everything by one variable. All right, so again, we'll work on those in class as pair deck. If you feel pretty good about it, there's at least some of these you can check off your box of some things that you feel pretty good about.